Let's start with uncertainty. Okay, the uncertainty principle is this. This is what you'll see written on the back of the exam. In a practical sense, this is totally useless. Okay, so the practical, let me write the practical version of this, but this is what I would give you on the exam. You need to be able to transform it. So you go change in x, no, it's not change in x, the uncertainty in x, it's really x. Momentum, P, is mass times velocity, and I just change this to an equal sign, it's easier, h over 4 pi. Okay, how do you know that it's this kind of question? You're going to see the words uncertainty is the most likely you'll see. You might see the word precision or the word accuracy. Any of those words or synonyms thereof, it's for sure this kind of question. Okay, the good thing about the hard thing about this question is the students freak out. The easy thing about the question is it's plug and chug. Okay, there's going to be usually one other variable in here, and that'll be some percentage will be given. So it'll be like, it'll say, for example, the velocity is known with a precision of 3.2%. And that percentage is just a multiplier on the left-hand side. So if you see a percentage given, it's very normal, more normal than not. And that'll be put in the left-hand side equation. So an example might be, you have a proton that is 0.010 nanometers from the nucleus, and it's traveling at 1/10 the speed of light. This would be kind of a typical type of example. And the velocity that's traveling at is known to 1.5% accuracy. Let's see what else might be given. Oh, this is cross this off. Okay, so it's traveling at 1/10 the speed of light. That's known at about 1.5% accuracy, and it'll say, what's the uncertainty in the position? Would be the question. So you see the word uncertainty, you'll see a precision or accuracy, in this case of the velocity. This is one of these styles of questions. Okay, so what they're asking for in this one is what looks like a delta x. It's really the uncertainty in the position. So what you would do in this kind of question is you would solve for x. That's what they want to know, the position. So you go h 4 pi, the percentage given, times the mass, times the velocity. And you go, well, h is a constant. Do you need to memorize h? No, where do you find it? Back of the test. Okay? 4 is just the number 4. Pi, where do you find pi? On your calculator. Okay? The percentage is 1.5. Change that to a fraction. What else? The mass. Where would I find the mass of a proton? Yeah, hopefully the back of the test. So if there's a question with a proton, it'd definitely be on the back of the test. I forgot if it's not always normally there because we don't always use protons. Let me see. I forgot. It's not on the practice exam section because I usually don't give it to you. Not that I've seen it yet. Oh, there it is. It is. Okay. This is from the back of the test as well. 1.673 times 10 to the minus 27 kilograms. And what else am I missing? 1/10 the speed of light. Where do I find the speed of light? Back of the test. It's called c. as a variable, and you don't need to memorize that either. 2.9979 times 10 to the 8th meters per second. I went off screen there a little bit. So this is literally a plug and chug. I just made it up, so I don't have the answer. You can find it at home. Okay? What kind of unit should I use here? SI units only. So the mass needs to be in kilograms, the velocity needs to be in meters per second, that sort of thing. Okay, so we'll be literally a plug and chug. The hardest part for most students is figuring out what variable goes with what. Once you do that, there is no tricky way or easy way to write this problem. It is just as is this type of problem. Okay? It's always the same. Okay, think if you have questions about that before I go on to the next thing. Rydberg is what I'll do next. Okay, any questions on the previous? Yes? Say it again. If you're given the radius and percentage, or really that's a distance, then you're probably solving for the velocity. So the two unknowns are either the x, which is position, or distance, anything in length units. And then the other variable is the velocity. One's given and the other one's always solved for. Yeah. So you'll either have the position and be asked about the velocity, or vice versa. This one had the velocity and you're asked about the position. Okay, Rydberg. There's also the Balmer equation. In my class, I never use it because the Rydberg is a more general form of the Balmer equation. So there's no reason to ever use the Balmer equation as far as my class is concerned. Rydberg looks like this. Something like this will be written on the back of the exam. It's the Rydberg constant. 1 over initial squared minus n initial squared minus 1 over n final squared. This also would equal h nu, or hc over lambda, the two equations that also go with the change in energy. Okay, this equation is only used in one scenario, and that's when an electron changes orbit. N is the orbit, or later you find out in the same chapter it's called the principal quantum number, but it's the orbit. This is the technical term for this sort of problem. When an electron changes orbit, say from orbit 2 to 3, 4 to 3, 5 to 1, whatever, any change in orbit, there would be this equation. This is the only equation you know for change in orbit. Yes?
What's that HB thing? Like,
what's this? This is Planck's constant times the frequency. It's one of the equations for energy given on the test. The other one is hc over lambda, Planck's constant times the speed of light divided by the wavelength. Okay? How would you use this sort of equation? We would set up the question, the electron changes orbit, its initial orbit was, say, 4, and then it falls down to the second orbit, for example. So we would say, what's the change in energy? You would say, okay, the change in energy is a Rydberg constant. Where would I find the Rydberg constant? Again, on the test, on the back of the test. If it's a constant, it's in the back of the test. So get familiar with the constants given in the practice exams, or posted, or in the practice exam manual. They're both all the same. Just so you know what's back there. 1 over initial squared, initially it's at 4, so 4 squared minus 1 over 2 squared. That would be the change in energy. By the way, for you math nerds out there, is this a positive or negative number? This will be negative. What does that mean about the energy? Yeah, if you get a negative answer, it means it's being released, which will always happen when you're falling down orbits from a higher number to a lower number. It will always be positive, conceptually and mathematically, when you're going from a lower number to a higher. So if you're going from 2 to 4, you get a positive number, that means energy is going into the system to cause the jump. If it's falling orbits, then that means energy is released in the form of light, whether visible or otherwise. Okay? If it asked you, hey, what's the frequency? You would say, okay, that number is just h times nu. H is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. times nu. So you could solve for nu. You can solve for lambda. So the variables are E, nu, the frequency, or lambda, the wavelength. Everything else is a constant or given. Okay, so those are the variables you could be asked to solve for. Again, plug and chug. Everything from the electrons chapter and many things from the gas chapter are literally plug and chug. So if you find the right equation, you just have to put everything together. Okay, any questions on Rydberg? Again, you recognize it because an electron changes orbits. Yes? That's right. So let me get a different color here. You will see in the reader and the text, there's a z squared here that we really don't use in this chapter. Well, because this chapter is everything is one electron. And Z represents, if you remember from way back, the atomic number, capital Z. So if you look at the periodic table, the only thing that has one electron is hydrogen. So Z is 1. That's the red number on these periodic tables, the one on the top. And so because Z is 1, 1 squared is 1, so we don't use it in this chapter. And if upcoming, not yet, maybe next class or so, we'll talk about other elements, and then Z will be a big deal. But that's why I've ignored it so far, but I did put it in the reader just for completeness. You'll see it being used later, but not on the exam too. Anything else? There was another question I thought? It was the same one. Okay. Hey, we're making decent time. Oh, we also did delta E. Wow, I did 2 and 1. I didn't know it. That was a twofer. Okay. The two-dimensional wave function, that'll be quick, and then we'll finish with the would I ask you the color? That's possible, but I would have to give you more information. So I would have to, Rachel, if you're in my class, did an example of this. I need to flip around to find it. I have it somewhere. But she also showed a slide that had a little bit of additional information. I'll show you what that looks like. And you'll see if you look through the practice test, I give you that when you need it, and it's usually not on the back of the test, it's actually in the problem. And it's a slide that has like a scheme, not a scheme, but a spectra of electromagnetic radiation, or spectrum. It would look like this. This is what Rachel should have showed you. So if you need to know, if I ask you what kind of light is given off, or what region of electromagnetic radiation are we in, you just calculate, in this case, the wavelength, or the frequency, whatever you're into if you're given this. You just look it up. So if you land here, it's microwave. If it's this wavelength, it's gamma, etc. Okay, so this would literally have to be given. Or something that looks pretty similar to it. You'll see it again on practice tests if it's this type of question. Okay, we're moving on to the two-dimensional wave function, or the particle in the box. There's not really a lot here. I mean, there's a lot to it, but we're not holding you to much of it. The particle in the box, that's where you've got a wave function that's a function of x. And the only quantum number really is n, the principal quantum number. And so this is when you have a particle limited to really two-dimensional space. What's the only thing you could really be asked here? Well, if I give you some sort of plot, let's say it looks like this, and this is psi of x versus x, and x goes from 0 to L, I could ask you, how many nodes do I have? You'd say 2, one here and one there if you have to label it. I could ask you n. N is 3, or the number of nodes, n minus 1 is the number of nodes. That's what I meant to say. This equation will not be given. That's something you need to know. That's also true in three-dimensional space. So for orbitals, it's the same idea. N minus 1 is the number of nodes. So this is something super important right there. I could also ask you what's lambda, and that would be 2L over n, or 2L over n is 3 in this case. So what does that mean? Lambda is the wavelength, and there's one wavelength and 2/3 of L, meaning one wavelength is right here. It's where you go through one repeat of a cycle, up and down, pressed in the trough. You can see it fills up 2/3 of the L length. And the formula is 2L over n. N happens to be 3. So those are the kinds of things I would ask you. There's very little to ask you about this section. More of the focus is in the three-dimensional wave function. Any questions before we do the three-dimensional action? Okay. For 3D, these are the orbitals. You should know really the shapes of all the orbitals. So the s orbital is spherical, the p is a 2 leaves, the d is 4 leaves, sorry, and then the f you wouldn't draw, but it'd be usually 8 or so. I could ask you to draw any of these. So for example, I could say, what's the 3s orbital? Or I would have a picture and you'd identify it. 3s orbital, well, s's are all spheres, so it'd just be a sphere. Likely I'd have you label the nodes. How many nodes are there? 2, n minus 1. Oh, we didn't do that. N is 3, I guess we already let that go. What's L here? Nope. 0, because L goes with S. So if you forgot that action, L starts at 0 and counts upwards, and that goes with S, P, D, and F, these letters. So make sure you got this down. This is very common for students to mess up. They'll get the wrong letter with the wrong number. Super common mistake. So don't let it be you. Let it be the people who are not here. Okay, there's 2 nodes. These are concentric circles inside the circle. Okay, the names of these types of nodes are? Radial. It's radial when they're circular. So when they're circular, they're radial. How many angular nodes are in any s orbital? 0. Oh, maybe I should ask what's the maximum number of angular nodes in an s orbital? 0. It's always 0. There's no angular nodes here. Okay, I could have you do a p orbital. Let's go to another slide. How about a 3pz, for example? Well, the pz, the p orbitals look like this. The pz is on the z-axis, so put it on the z-axis. What's n here? 3, it's the first number. L is? Yeah, it's the letter P or the number 1. Nodes? 3 minus 1 or 2. N minus 1 is the number of nodes. Okay, does a p orbital have any angular nodes? Yeah, it's born with 1. So this is an angular node right there. Can a p orbital have more than 1 angular node? No, it's always 1. S is always 0, P is always 1, D is always 2, etc. Follows that pattern. Okay? All right. Can a p orbital have radial nodes? Yes. Can it have 0 radial nodes? Yeah, a 2p orbital would have 0 radial nodes. And then it can go up to infinity. So the radial nodes are just the remaining nodes. One of the nodes is angular. It always has an angular node. The second one will be radial. And that is always a circle inside the lobe. So this is a node there as well. And specifically, that's the radial node. Both the top and bottom count as 1. Okay, so that would be the 3pz with both nodes labeled. Any questions on that? If not, I'll try a D. Okay. Let's do the 4d x squared minus y squared. All right, first, what's n? 4, because that's 4. What's L? 2, that's for the letter D. So the number of nodes? 3, n minus 1. Okay, so d orbital, the dx squared minus y squared, is that on or off axis? On. If you see a squared, that's on axis. So it's on the xy axis. So it looks like this. Make one of these a y and one of them an x. There we go. There's the dx squared minus y squared. How many angular nodes for a d orbital? 2 and always 2. They're right here. They split it or bisect it, sort of. So that and that, they're both angular nodes. 2 of them. It's always born with 2. No less, no more. Again, the pattern. S has 0, P1, D2, etc. Okay? Can this have radial nodes? Yes, everything can have radial nodes. It can have 0 or more. This one, because it has 2 angular nodes and there's one more, the additional have to be radial. The radial nodes, again, are just circles inside the lobes. So it looks like this. Just draw something that kind of looks like a circle. And this, what I drew just now in black, is the radial node. That's the 3rd node. And there's your 4d x squared minus y squared orbital. I'll zoom in a little bit. That's a little zoomed out. There we go. Okay. Yes? Which one? The dz squared would be born with 2 angular nodes, but I'm not going to ask you to draw it. It's not drawable for a normal human. So I wouldn't ask you to draw the dz squared nodes. They're conical looking. Yeah, so forget about it. Yeah. Yeah.
So on a test, if it asks for n Isabel, when would you list all the values or just give the number of the total values?
Okay. Let me do that if nobody else has a question about this. Okay, that transitions nicely to quantum numbers. Okay, which is our last topic for the night, I think. Yep. Okay. There are several types of quantum number questions. Let me just list them out first before I get to yours. I'll just put QN for quantum numbers. What are the styles of quantum number questions? Well, there could be the drawing question, because you need to know quantum numbers to draw stuff. That's what we just did. Okay. You can do like, is it allowable or forbidden? So we won't necessarily do all these examples, but I did one in class last time where we did a quantum number, and I said, is this allowable? For example, we did 2D. 2D is not allowable because, what? L is 2 and N is 2. You can't, N and L cannot be equal. L must also always be less than N. So that's a typical question like there. And then there's, what are all allowable quantum numbers? So what are all allowable quantum numbers? That's the kind of question you're asking right now. Then you would list everything. A variant on that is how many, what's the number of electrons given a certain set of quantum numbers. So if these are the quantum numbers, what allowable quantum numbers are there? And then there could be a combination of these, and I typically do those in tabular format if it's a combo question. A tabular sort of question. Again, look through practice exams so you can kind of see what the heck I'm talking about. This one, here's one form. This is winter of 2016, page 62. This is an all allowable kind of question, the third one. Okay. There's, oh, here, the one right below it. This is not put in a table form, but part D is drawing, and then these are just different, like how many nodes, what, or like it's just a combo sort of question. There's other ones like that. Just want to show you one more so you can kind of see what they look like. There's other types of quantum number questions that we haven't got to yet, but they involve the electron configurations, more complicated than what we've done so far. So you wouldn't see the couple other styles on this exam. I just want to look really quickly, see if I see another table sort of question, but it's not loving on me right now. But I would just say for now, look through the practice exams, and you'll see plenty of different styles of examples that you can kind of study through. Quantum numbers are pretty much guaranteed on an exam. Yeah, it's somewhere. Okay. Well, hold on. Yeah, not going to find it right now. Okay, so you asked about the all allowable, so let's do an all allowable sort of question. Well, it could look like this. So, like n is 4, so write all allowable quantum numbers. So, if we're doing all allowable, you'd go, okay, if n is 4, then the all allowables, L could be 0, 1, 2, or 3. Then M sub L, if L is 0, M sub L is 0. If L is 1, 0 plus or minus 1. If L is 2, 0 plus or minus 1, plus or minus 2, plus or minus, oh, that's it. And if M sub L, if L is 3, M sub L goes up to plus 3, between plus 3 and minus 3. Yes? Okay, you could go the other way. So M sub L is sustained. It's all allowable, but there's only one value of M sub L. M sub L is whatever, minus 2. You can make up problems with your friends, okay? Just whatever. Minus 2. So it's all allowable, but there's only one M sub L in this case. So then in this case, L. Okay, then you have to think through. When it's going backwards, it's a little harder. So I usually start with what's the smallest value of L that could give a 2. Okay, let's check. People are saying 2. Well, if L is 2, M sub L could go from minus 2 up to positive 2. That would work. Let's just check 1 just in case. If L is 1, it goes from minus 1 to 0 to plus 1. So it wouldn't include negative 2. So that's in the garbage. Then you'd have to ask, can it be larger than 2? 3. Does 3 work? Yeah, because it would get minus 3 to positive 3. So it would go through minus 2. Minus 3, minus 2, minus 1, 0, 1, 2, 3. So it can go up from 3 to infinity. Then n. Again, I do like to start with the smallest. What's the smallest possible value for n? 3. Yeah, if L is 2, n has to be bigger than that. If L is 2, could n be 4? Yeah, anything larger than 2 will give 2. And 4 also works for 3. So it can be 3, 4, 5, dot, dot, dot. Does that kind of make sense? That's a pretty common all allowable question. Yeah, and you saw that in the example I showed on the screen in the table. Table format or multiple choice is pretty classic for one of these. All right, so these are the styles of quantum number questions you'll see on practice exams because they're the only ones that we have thought of. Okay. All right. Yes, way in the back. Number of electrons? Yeah. Give me a number between 1 and 4. 3. Okay? See, you and your friends can make this up. So, if you're doing the last one, the number of electrons, I pick a random number, 3. I want, what's the total number of electrons? There's kind of 2 ways to word it. The first way is the total number of electrons. So what you would do is you're going to do an all allowable first. So you're going to go L is 0, 1, 2, oh that's it, 0, 1, or 2. Then you go M sub L. So you go busting out all your quantum numbers. If L is 0, M sub L is 0. If L is 1, m sub L is 0 plus or minus 1. If L is 2, m sub L is 0 plus or minus 1 plus or minus 2. Then you want to count the number of orbitals, or really the number of m sub L values. So there's 1 digit here, so 1 orbital. There's 3 digits here, 0 plus 1 minus 1, so 3. And there's 5 here, 5. Okay, so you got to do that count. How many electrons can fit in each orbital? 2. So in 1 orbital I could fit 2. In 3 orbitals I could fit 6. In 5 orbitals I could fit 10. Add that up, 18. The total number of electrons that I could fit in n equals 3 is 18. So it's a count of the m sub L values times 2. One more time, it's a count of m sub L times 2. A variant of this, a very slight variant, could be how many spin up electrons are there and how many spin down electrons are there. What would you answer? Spin up, 9, and spin down 9. So half are spin up, half are spin down. So I could say how many spin down electrons are in n equals 3, and you would say 9. So again, you count the m sub L values, multiply by 2, and that's the total. Half is spin up, half spin down. Yeah. Can I see that? I guess this is a table I was just looking at. Okay. Same test. Okay, I wanted you to fill in the blanks. This is an all allowable question. And I gave you the m sub s values here. Okay, let me ask the audience. What is the connection between m sub s, the 4th quantum number, and the other 3? Nothing. So this is meaningless right here. This tells you nothing about how to fill in these blanks. N, L, and m sub L are connected. Like L is smaller than n, m sub L is between minus L and positive L. This is randomness. Okay, so let me pull the audience. What do I do when this is blank? And I want all allowable. Plus a half and minus half. Is that okay? Again, no connection to the other 3 quantum numbers. The 4th one is fully independent. Okay? All right, let me pause right there. Folks that want to go home, get the heck out of here. And I'll take specific questions in about a minute or so. You can just stay where you're at. As soon as it quiets down, I'll start taking your questions.